Okay, so we're back to talk about critical numbers. So I just wrote a definition here, or just a note. So critical numbers are important x values on a graph. They will give us information that's needed to find maximum and minimum values, as well as asymptotes and inflection points. So we talked about the maximum and minimum. So the hills and valleys are here. So this would be a local minimum, and this would be a local max because it's at a hill, and a local min. Now, there are actually, how to find those points when you're just given an equation and not looking at a graph is to set the derivative equal to 0. And the reason that is because the derivative is the slope, and at those points we're coming down, so the slope is negative. Then we switch to going up on the other side, and at that point, right in the middle of switching from down to up is a 0, a slope of 0. Same here, this goes up, 0, and then down. So it's sort of like if you're in your car and you are going to reverse your direction. So instead of going forward, you're going to go backwards. In between that, you're stopped. You have to stop and then change directions. So that's what's happening here. So it goes decreasing, stops, and then increasing after. So the derivative also tells us about where the function is increasing and decreasing. Okay, so those are all critical numbers. The other place there are critical numbers are at the asymptotes. So here, whatever x value this is, say this is x equals 2, then the asymptotes are critical numbers found by setting the denominator, the bottom, of the derivative equal to 0. So we've got a derivative that has x's on top and on bottom. By setting this equal to 0 and solving for x, we're finding the values that don't work in the function. And when something doesn't work, how we see that on the graph is at an asymptote. I just put an A here. This could be any x value, but there's 2 of those that we would find. Now, the only other type of critical number that we can get on a graph is sometimes when a curve is curved, so this is sort of curved down, we say that that's concave down. And then on this side it's concave up. Right in between where it switches, that's called an inflection point. And that point is also a critical number. So there's sort of 3 types. So in green I put the local max and min. That's found by setting the derivative equal to 0. And these inflection points also come from that. And then the asymptotes are when there's a fraction. Now we're not going to do this type right away. We're going to start that the next class, but we're going to see these local max and min types and inflection point types this time. Okay, so basically we're going to say find the critical numbers and determine whether they are local max or mins or neither. And if it was neither, then it ends up being this inflection point. Okay, so the steps are find the derivative, set equal to 0 and solve for x. put the critical numbers on a number line. And test each interval for increasing and decreasing. So basically we're going to put a critical number here, whatever it is, and then we're going to test. We're testing whether it's positive, which means the graph is increasing, or negative if the graph is decreasing. If it goes up and then down, then this would be a local max, because that means the graph is going up and then down on the other side. So right at the A, that would be at the top of a hill. We could also have the scenario where we go down and then up. So this would be a local min. Or something like this. We go up and then still up. So this would be an example of neither a max or min. And that could also be minus minus, down and then down again. Okay, so example 1. Okay, so we have something like this. Step 1 is take the derivative. So derivative of x squared is 2x. Derivative of minus 4x is minus 4. Derivative of 5 is 0, so we don't have anything. So step 1. Step 2 is take the derivative, set it equal to 0. And we just solve for x. So x is 2. Once we have that's our critical number. So if all we were asked for was a critical number, that's it. We put our critical number on a number line, and then we're going to test. So what are we going to test? We're going to choose the number smaller than 2. Any number. Could be 1, 0, so 0 is usually an easy one. And we're going to test a number bigger than 2. 5, 10, 3, doesn't matter. Let's put 10 in. It's easy to plug in. So what are we plugging these into? We're testing the derivative, because that tells us whether something is increasing or decreasing. So when we plug this into the derivative, this is 2 times x minus 4. So 2 times 0 minus 4. We get negative 4. This is negative. We don't care the number, but it's just saying on that side the slope is negative. And then on the other side, 2 times 10 minus 4, we'll have 20 minus 4, which is 16. That's a positive number, so positive. Now we don't plug the 2 in, because what happens if we plug the 2 in is we get 0. That's how we found it. Right? So that means it's one of these situations up here. That's all that the 0 is telling us. So this goes down and then up, so that x equals 2 is a local minimum. We could also say from here that the function that original function decreases before 2. And to write before 2, we actually say negative infinity to 2. So that's negative infinity all the way to 2 with round brackets. That's an interval. And it increases after 2. So we would say that's 2 all the way to infinity. And we're going to need this later, so I'm just going to write it down now. On the homework I don't ask you to do that part, but it is good to see because we do have to do it later as another part of the course. Okay, so say we had something like this. We take the derivative, and then we set that equal to 0. So this is not a trinomial, so but it is a quadratic. We could say what's a common factor? Well, they both have an x. And then this is two answers. This is x equals 0 or 3x plus 4 equals 0. So these are critical numbers. We can put them on the number line. Put them in numerical order, smaller number first. And then we're going to test in each interval. So this is, if you put it in your calculator, negative 1.33. So we need a number smaller than that. So let's say negative 10. In between, let's say negative 1. And bigger, maybe 1. And we plug each of those into the derivative. Again, we don't plug these numbers in. They'll just give us 0. We want to plug in numbers in the different intervals. And we're plugging them into the derivative. So 3 times negative 10 squared plus 4 times negative 10. So 300 minus 40. I don't even need the answer here. I can see that that's positive. That's 3 minus 4. I can see that that's negative. And that's positive. So most of the time they do switch from plus to minus. So this is positive, so it goes up, and then it goes down, and then it goes back up. So up here, this would be a local max. So we would say a local max at x equals minus 4 over 3. And a local min at x equals 0. That's at the bottom, so that would be a min. And just to add the intervals of increasing and decreasing, we would say it's increasing wherever it's positive. So this is negative infinity to negative 4 over 3. And it's also increasing over here, 0 to positive infinity. And we show that with a union. That's a just set notation. So that's called a union. It means add to it. So this plus this. And then it's decreasing in between minus 4 over 3 and 0. Always the small number first and then the big number. So this is the kind of information. And if we had this a bit more curved, actually that would be the shape of the graph. The graph of this is going to look something like that. Okay, which we're going to see later. Okay, so if we did this next one, oops, cubed, and plus 0. So 4x cubed minus 4x equals 0. The common factor we could factor out here a 4 and an x. We're left with x squared minus 1. This is a difference of squares, so this can be factored further. So there's 4x. This is x. Square root of 1 is 1, plus 1, x minus 1. Remember this one, x plus 3, x minus 3, that's a difference of squares. The same idea here, x plus 1, x minus 1. Square root of 1 is 1. So here we actually ended up with 3 numbers. So 4x equals 0 gives me 0. X plus 1 equals 0 gives me negative 1. And x minus 1 equals 0 gives me 1. So we have 3 numbers to put on a number line. Put them in numerical order, the smallest one first. So we're going to test the derivative with some number smaller. So let's say negative 10. And then in between these, we're going to have to use a decimal, so negative 0.5. So you could use your calculator for that. Positive 0.5 and maybe positive 10. It doesn't have to be, you could put 2 in if you wanted to, but it could be any number as long as it's in that interval. If you accidentally plug these numbers in, remember, they just give you 0, so it doesn't give you a positive or a negative number. All right, what was our derivative? 4 times x cubed minus 4 times x. So I'm just going to write them all out, and then I'm going to figure them out on the calculator. I can see that this one's positive. That's going to be 4,000 minus 40. This one is going to be negative 4,000 plus 40, so that one's negative. And this one, oh, I missed one too, didn't I? I missed the 0.5. Okay, so 0.5 cubed. This isn't my usual calculator. Oops, got something weird going on. 0.5 cubed times 4 minus 4 times 0.5. So this one gives me negative 1.5. It doesn't matter the answer. The other one, negative 0.5 cubed times 4, and that minus and a minus is a plus, 4 times 0.5. So just carefully putting them in your calculator, that gives me a plus. Okay, so down here this one was a negative, that one was a positive, the 0.5 was a negative, and the 10 was a positive. They're out of order here, but that's because I missed one. So it goes down, negative, up, down, until we get to 1, and then back up. So local minimums, there's 2. X equals plus and minus 1. These are both at the bottom of valleys. And then this one is at the top. So local max at x equals 0. And you could list the increasing and decreasing intervals again. We might as well do that. So increasing from negative 1 to 0 and from 1 to infinity. Those are where the pluses were. And it's decreasing from negative infinity to negative 1 and from 0 to 1. Okay, so suppose we had this equation, so we take the derivative, 6x squared, that's it. So set that equal to 0, and that just gives me x is 0. I mean, you can work that out. Sometimes people aren't sure, but square root of 0 is 0. So we just get 0. That's our only critical number. Put that in the number line, and we want to test the derivative bigger and test the derivative smaller. Let's say plus and minus 1. Those are bigger and smaller. So f prime of negative 1 is 6 times negative 1 squared, 6. And at 1, 6 times 1 squared, 6 times 1 is 6. Those are both positive. So this goes up and then up again. So this is no local max or min. And if we wanted to write the interval that it's increasing, it's always increasing, so it's increasing from negative infinity to positive infinity. Okay, so you can have that situation. And if we go back to that first sheet, that if we were to draw this graph, it kind of looks like this. This goes increasing and then increasing again, but it's going to have a curve to it. So it's not a max or a min. Okay, we'll do another example. Okay, so take the derivative. And then I'm going to set this equal to 0, but I think I'll use the quadratic equation because of that 15. So x equals minus b plus or minus. I'll just write it out. So minus 4 squared, so this is 16, minus and a minus is a plus, 180 over 30. So minus 4 plus or minus 196 over 30. Square root. And that's 14. So minus 4 plus or minus 14 over 30. So x equals minus 4 plus 14 over 30, sorry. Or minus 4 minus 14 over 30. So that's 10 over 30, which is 1/3. And this one is minus 18 over 30, which is minus 3 over 5. So on the number line, that one would come first, and then 1/3. Now if you put in the calculator, this is 0.33. 3 divided by 5 is 0.6. So in between we could pick 0, because that's a negative and that's positive. So in between is 0. Bigger maybe 1, and less minus 1. And we want to plug those into the derivative. So that's 15 times minus 1 squared plus 4 times minus 1 minus 3. It's going to be plus. 15 times 0. I can see that that's minus. And the 1. So this will be 15 plus 4 minus 3. That's also plus. So it goes up, down, up. So the local max up here. And local min down here. Okay, so that's if you used the quadratic equation. You would do the same thing. You can convert these to decimals if they don't work out nicely. And, you know, these were nice fractions. They worked out okay, but if you couldn't do the square root, you would just get a decimal. Maybe we'll try one like that. Okay, I'm just going to think of something that maybe won't work out nice. No, probably if I just make the numbers up, they won't. Okay. Oh. Let's try that. Okay, we'll see what happens. It doesn't matter what happens if it doesn't do what I wanted it to do. It's going to do something anyway, so we'll find an answer regardless. So 3 times 4 is 12x squared. 2 times 2 is 4x minus 3 plus 0. All right, so quadratic equation. Minus b, it's b, plus or minus square root of b squared, minus 4 times a times c, all over 2 times a. All right, so let's see what happens here. This will give me 16 plus 144 for 24. So this is 160, so 4 plus or minus square root of 160 over 24. So square root of 160 does not work nicely. So what you would do is put that in your calculator. Keep 2 decimals. Okay, I'm always going to just say keep 2 decimals, so if you're in doubt. So this would be our 2 answers. One is 4 plus 12.65 over 24, and the other one would be 4 minus 12.65 over 24. So let's find the decimal for this. So the first one, and then the second one, 4 minus 12.65 divided by 24. Okay, so there's my 2 critical numbers. Put them in numerical order. And we can test 1 in between 0 and -1. And our derivative was 12. That's positive. Oh, 0. That's 0, 0 minus 3 is going to be minus. And the answer, again, doesn't matter. Just whether it's plus or minus. So this is 12 minus 4 minus 3. That's positive. 12 minus 7. So it goes up, down, up. Max at the top, and min at the bottom. So local max at x equals negative 0.36, and local min at x equals 0.69. Now, to be exact, we would actually keep the square root of 160, but for any of our purposes, rounding it off to 2 decimals will work. If you needed it to be more accurate, you'd either keep more decimals or keep it as the square root until the very end, but this works fine. Okay, so that's basically critical numbers with just polynomials. Okay, and then, so what we'll do next is critical numbers with fractions. Okay, so we're going to see that example next.